Today, we're going to take a look at data breakpoints. Everybody's familiar with a standard breakpoint. You double-click on a line of code, you start your debugger, and the system stops at, or in some cases very slightly after, that line of code is executed. We see that right here. Breakpoints are commonly used in debugging. It's the most common tool. A data breakpoint is a breakpoint that stops on the reading or writing either generally or of a specific value to a memory address. To demonstrate this, we have a quick demonstration. Shown here is what we want to happen. Essentially, we're going to cycle through 3 different LEDs, red, green, and yellow, periodically. However, I've created a version of code that has a critical bug in it. And for this reason, these lights will not cycle on this code. Let's take a look real quick at the main function. System Initialize simply sets up some of the registers for the chip. The system is very simple. It consists only of 3 LEDs hooked up to a PIC that are through current limiting resistors, and the appropriate pull-up resistor on reset and capacitors necessary to make the chip work. So there's nothing complicated here in this hardware. We come through our system initialization. We have 3 global variables that we've created. Delay loop, which I've marked as volatile because it's used at the bottom of a loop just to take up time. We didn't want the compiler to optimize this out, so I put volatile on it so it couldn't just say, oh, this does nothing, and skip it. Timer counter. Essentially, we're going to go through this loop, and our goal, every time we come in here, we're going to increment that counter variable. If the counter is greater than 10,000, we'll return 0. We'll set it back to 0 and return 1, meaning, oh, this time has passed. Otherwise, we'll return 0 after just having simply incremented it. When we come through here, this time to change lights, if it returns the 1, meaning it got up to 10,000, we'll take a look at the current light variable. We have 3 values, red, green, and yellow, 1, 2, and 3. And that will go into this current light variable. One thing to note in this example is that there are a variety of bad programming practices here, and that was on purpose to try to create something that could demonstrate the sort of bug we needed in as few lines as possible. There are a whole bunch of things that I would normally do that would actually make this bug disappear or not exhibit the way that it does. But, this is not an example in a variety of different ways of good programming. You can see that we initialize current light coming in here through main. Normally you would do this up here, but it breaks the bug that I'm trying to introduce because it actually puts the variables separately apart. I'm giving a little hint as to what the bug is here. But we come in here and we look at current light. If it's red, which is 1, we say, okay, next light to turn on will be green, and we set the appropriate ports to energize that LED. If it's green, we set a different set of ports and we say the next light to be set as yellow. If it's yellow, we set the appropriate lights for that, and we go back to the red light. So ultimately, what we expect to happen is this guy to go into a tight loop and increment timer counter till it gets to 10,000, at which point this function will return a 1. We'll come into this if through the switch case and cycle from one light to another, and we will do that in a constant sequence. And again, here down at the bottom, we have a delay that I've just introduced to make the lights run slow enough that we can visually see that happen. However, if we run this code, nothing is happening. Do we ever get time to switch lights? Oh yeah, okay, so I used a standard breakpoint here. I put a breakpoint in. Maybe we weren't getting through this. No, we are. What is the current light? Oh, that's weird. It's a 0. Where could my code have set that value to 0? Current light is set right here, and it gets set to green light. It gets set to yellow light. It gets set to red light. None of those values are 0. That's strange. So you might ask yourself, well, maybe something bad happened here, and this initialization didn't happen. So let's do a reset, and we'll hit that breakpoint right here. So at this point, this initialization should have happened. Let's take a look at current light. Well, it's 1 right there. It's 1 right there, so it definitely got set. So if we let this run, we come down here. So we went through this enough times that this returned a 1. Now current light is set to 0. The only place in this function that sets it is here, here, and here. So let's reset. Let's do a reset and run. So we hit that. We'll hit go again. And we never hit any of these guys, yet it's set to 0. How is this possibly happening? And if you looked closely at the code, you probably could figure it out. If you looked at the compiler warnings, which we should always do, but sometimes don't, you could definitely figure it out. So let's take a look real quick, and let's use something called a data breakpoint. So what I'm going to do now is set a data breakpoint. Let's take a look at the variable that we're interested in, current light. That's at address 856. We're going to go up here to debug, new breakpoint, and we're going to say data. And let's take a look and say, where is that variable written? And what's going to happen is we're going to get a break every time current light is written. So let's reset now and say go. And you can see we stopped right here. Why is that? Well, current light just got written right here. So that's not a terribly interesting one because that's the one value we want. Let's see, where does it go to 0? Up here, which is really, really weird at first glance because this variable shouldn't get passed in here. Did we pass the current light to time to change lights? No, we passed timer counter. So now let's go back and take a look at the output from our compiler. This is the compiler warning that we missed. We mixed types. We passed a pointer to a uint16, but this function expects a pointer to a uint32. So when we thought we were pointing to timer counter, we were pointing to the beginning of timer counter, but instead of adjusting 2 bytes, this increment is going to adjust 4. So we were actually writing over this byte and whatever byte would have happened to have been past it. So this is a case where a data breakpoint was able to stop immediately at the value that the place where the variable was being written, even though in fact that variable doesn't show up anywhere in here, and we didn't intend to directly reference it. These kind of data breakpoints can be very useful for things like tracking down stack overflows. For instance, if you know the location of your stack, you can set a breakpoint very near the end of the stack and say, hey, this value should only get written perhaps once at initialization. We really don't expect to use up all of our stack space. So if we actually write all the way to the end of the stack, I want you to break, at which point typically you can say, oh, okay, we just entered some new function, or we had a string copy that went off the track, or something was wrong with a printf, or any of a variety of processing functions that use self-incrementing pointers. So that's just a quick demonstration of what a data breakpoint can do for you. Let's fix our bug now and execute again. And actually that breakpoint is still in there. So let's go to Window, Debugging, Breakpoints. Get rid of that data breakpoint because we don't want to hit that again. And lo and behold, our lights are blinking. So this is a very simple example, but it really scales exceptionally well, even to the cases, in some cases, where you have real-time operating systems with multiple stacks or queues or a whole variety of different type things. One thing I will note that I did not show here is that you can do a more complicated version of a data breakpoint that allows you to say a specific word or a specific byte. Now, the funny thing is, you might think, oh, I'm looking at a byte-sized variable. Let's go ahead and put our bug back in here. I'm going to go ahead and put a breakpoint in here. And data. Okay, I know my symbol, current light, is an 8-bit value. So what should I shoot? I could do write on a specific byte. And I'll say the value that I want is 0 hex, because that's the weird value that I'm getting. If you have a situation, say, where you have a state machine, and there's some state that it should never actually end up in, yet it does, your state machine variable, you could set it to that particular value. So let's do a reset and say go. Now the weird thing is we're not hitting that breakpoint. Why is that? Well, it's because we told it, I want you to break on a byte write. But if we look at the nature of this bug, this is an int32. I'm running on a 16-bit microcontroller. So when we go to dereference this pointer, we're actually going to do it in two 16-bit chunks. So now I got to go to Window, Breakpoints, and let's edit this breakpoint, and let's say write specific word, because it turns out that we're actually going to be writing a 0 word, not a 0 byte, and that's an important difference. And lo and behold, we see it, and it hit it right there immediately. So you need to be very careful when you say byte or word. Sometimes it can be better to just pick just say any write until you know exactly what's going on. Because if you limit yourself, and it's the result, as we have here, of some incorrect pointer dereferencing, then even though it's a byte-sized variable, you may actually get a word right, at which point your data breakpoint wouldn't go off. So that's kind of an important subtlety to understand about the way that these things work. If you like this video, give me a comment down below. If you're interested in learning about some of the other breakpoint types, event breakpoint types, sequences, things along those lines, there are microchip produced videos out there. Or if you'd like to see me conjure up another example like this that shows one of the other breakpoint types, let me know in the comments. I'd appreciate it. Broadwell Consulting Incorporated provides help developing medical devices with a focus on developing embedded firmware, which is compliant with IEC 62304, ISO 14971, and ISO 13485, as well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting.